Hi everyone, in today's video we are going to touch upon the introduction towards electrolytes. Okay, so electrolytes, what about it, right? There's two kinds of cell. So I'll put it this way. There's voltaic cell and there's electrolytic cell. And why I would relate them together is because in a way they're like somewhat opposites. The voltaic cell, the function is to produce electricity, whereas electrolytic cell, it uses electricity to break down a compound. So voltaic cell, when you do the voltaic cell, it generates electricity, right? So that's why the energy change is from chemical energy to electrical energy, whereas electrolytic cell is we're using the electricity that we get from the battery per se to break down a compound. Okay, so that's why the energy change is from electrical energy to chemical energy. Now, by definition, what are electrolytes? Electrolytes are basically a substance that's able to conduct electricity in a molten or even aqueous state of form and undergo chemical change while doing so. So what's the difference between electrolytes and electrolysis? Now, electrolysis is basically the process of breaking down a chemical compound using electricity. So same thing lah, the function of electrolytic cell. It's basically to use electricity to break down a compound, whereas the definition of electrolysis itself, it is the process of breaking down a chemical compound by using electricity. So remember, electrolytes is the substance inside that's able to conduct electricity in molten or aqueous state or form. Here's the thing that why this is important. You have to differentiate between what a metal is and what an electrolyte, what electrolytes is. Why isn't pure metal an electrolyte? So because they can only conduct electricity in solid and molten. While they still have molten, but the condition that we want is it can conduct electricity in a molten and aqueous state, not solid and molten. We want molten and aqueous. Okay, another thing about metal is when it conducts electricity in these two states that are already not within our criteria, when it does not undergo chemical changes. Okay, so that's why it's not an electrolyte. So what do you call pure metal? Instead of calling it an electrolyte, we call it a conductor. This is pure metal. Okay, so apparatus set up for electrolysis, just a quick touch upon, there's two. There's one, the molten version, and there's the aqueous solution version. So that's why, if you notice, the molten, we use a crucible whenever we want to do the sort of experiment, because when we need to heat it up, we need to use an apparatus that could withstand the high heat. So crucible is made out of ceramic, so it can withstand the high temperature. When it comes to the aqueous solution, since it does not require heat, so that we use a beaker because no heat is required or no heat is used. Okay, what is molten and aqueous? Quick revision. A molten is basically solid that's heated, melts to liquid. The solid, it melts, turns into liquid. So liquid is in a molten state. Whereas an aqueous, it's like it dissolves in water. So let's say you put in sugar as a solute and H2O as a solvent, and eventually when you mix it, it forms like an aqueous solution, an aqueous sugar, or you can also say it's a sugar solution.
Let's check out the comparison between the conductor as well as the electrolyte. So conductor is able to conduct electricity in both solid or molten form, but then electrolytes, it is molten and aqueous. Okay, and a conductor does not undergo chemical changes, whereas electrolytes does undergo chemical changes. Now, example of conductors are all metals and basically carbon as well. Now, another name for carbon is graphite, and take a look at electrolytes. Everything that is an electrolyte is basically an acid, alkali, and ionic compounds. And a quick revision, ionic compounds is basically metal and non-metal. It's the strong electrostatic force between these two. Next one is when it comes to conductor, it's able to conduct electricity within these states because there's the existence of the free moving electrons, or you can say the sea of delocalized electrons that are present. Whereas the electrolyte, they can conduct electricity because it has free moving ions. All covalent compounds are non-electrolytes because all covalent compounds, think about it, cannot conduct electricity. All ionic compounds are electrolytes. Okay, so but then there are only electrolytes in molten and aqueous solution. All acids and alkalis are electrolyte dengan syarat within the condition that it is not dry or glacial, or there's no presence of organic solvent in order to ionize the acid and alkali. Because remember, acid and alkali does not ionizes in organic solvent. They ionizes in H2O to produce those H plus ions or OH or hydroxide ions. For example, sodium hydroxide in tetrachloromethane or even in ethanol, it's a no-no. It won't be an electrolyte. So if someone tanya, determine whether it is an electrolyte, we have to view it closely. So molten glucose, it doesn't sound like it has any the name metal in it, right? There's no metal name in it. So it's safe to assume it is not an electrolyte. It's confirmed covalent compound. There's no metal at all. Okay, next, zinc chloride solution. Right? So it's ionic compound in a solution. So yes, aluminum oxide powder, while it is an ionic compound, it is in the state of solid, so it's not. Hydrochloric acid, they didn't mention it's dry or even glacial, so we can safely assume it's a solution as well. Okay, so this is right.
Here's a popular SPM question. So now they'll ask, okay, why does the bulb not light up when the solid, which is the lead bromide, is used? So when it's solid, right, you can answer it like this. When it's in solid, the Pb2 plus, the lead ions and the bromide ions are fixed in a lattice, not sure, structure, and they are attracted by strong electrostatic forces. Therefore, there are no free-moving ions to carry the charge. This is why the solid for lead bromide does not conduct electricity, whereas when it lights up is because the electrostatic force between the two ions are overcome. So therefore, the ions are able to move freely to carry the charge. That's why the molten for the lead bromide is able to conduct electricity. And if you look at over here, identify whether the following substances are electrolytes or not. So these are basically the same thing what we've learned. So they have to be something that's acid or alkali, but not in glacial or dry, and not in an organic solvent. So if you look over here, and ionic compounds are electrolytes, remember? So if you look over here, the reason why this is not an electrolyte, because this is basically solid, right? And then if we look over here, molten tetrachloride, this is not an ionic compound. Glacial methanoic acid, it's an acid, but it's glacial, so therefore it's wrong. Let's look now at the strategy when dealing with electrolysis questions. So number one, step one is to label the positive and negative terminal. Now this is decided by the battery, or you could say dry cell. Now if it's the longer straight line, that one's the positive side, then the smaller one's negative, so here must be the positive side, here must be negative. So the anode and cathode is decided by the which one's the positive and negative terminal as well. And when it comes to electrolysis, the positive terminal, which means the positive terminal is basically the anode. Okay, the positive is the anode and negative is the cathode. Anodes are positive, cathode is the negative. Okay, so number two, you have to identify what are the ions present in the electrolytes. So when they say molten zinc ion, then that means there's only zinc ions and also the oxygen ion. If they say like zinc oxide solution, however, then you have to take into consideration that solution means there's water, so there's H2O. That's different, so let's look at the molten one first. So since they say it's molten, lead bromide, so there's only the lead ions as well as the bromide ions. So where will the ions go? So if this is your positive terminal, right, and if this is your negative terminal, eventually opposite charges will attract. So all the negative charge ions, the anions will go to the positive terminal, and the cation will go to the negative terminal. And negative terminal is the cathode. So the cations will be attracted to the cathode. So all ions move to positive or negative terminal because they want to be discharged, because positive and negative equals to neutral, right? So discharge basically is they want to be neutral. So for example, so if chloride ions, they want to go and change into chlorine. Sodium ion, they want to change into sodium. Okay, so number 5 is to write your half equation. Number 6 is use your half equation to do an apple-to-apple comparison. You have to compare it between the left side and right side, and then state out your observations. Now, observation plus color, these are very important. So let's say if your product is metal, right? So you can see a solid, right? So what's the color of the solid? So if it's a gray solid, then gray solid is the positive. If it is a non-metal and you see a gas, so you just mention what's the color of the gas. Is it a grayish yellow gas that's produced? And you have to mention where is it produced, at the positive terminal, at the anode, or the cathode. Okay, so all metals are basically gray solid except for copper, which is brown solid. Okay, so this one is normal periodic table when it comes to the colors. And the oxygen and hydrogen are obviously colorless gas bubbles. And here are some extra information. Okay, so here's an example We're using a crucible, so means it's molten, and the ions that are present are only sodium ions and chloride ions. Opposite charge attracts, right? So here we have the positive terminal that are attracted by the negative ions. So in that case, the positive terminal based on the battery here, the dry cell here, we can see here is the positive terminal, negative terminal. So here's the anode, is the cathode. They didn't specify which electrode we're using here, but we're going to learn that in details very soon. So positive terminal is the anode, and as you can see, what are the charges over there? The ions that are attracted to the terminal is chloride ions, and it's getting discharged, right? So you just write your half equation for it. And then your half equation, from there you can manage to form your ionic equation. Make sure the electrons are the same. So this is wrong because I am supposed to times this part by 2. So what you'll get eventually, it's 2Na plus 2Na. Alright, okay, observation, greenish yellow gas is released at the anode. Why? Because it's the chlorine. Gray solid is deposited at the cathode. Because we can view our half equation here. From half equation, we can see it is from the ions that is within the liquid to a solid sodium. So this means that gray solid is deposited. So that's why final product, if they ask you, then you can specify what it is. So it's chlorine molecules, but it's better to say chlorine gas is produced. You can specify even further at the anode cathode. Okay, then you can say the sodium metal instead of saying sodium atom, because sodium metal sounds way better. Alright, so here's a quick reminder for a voltaic cell. You can remember then, if voltaic cell anode is negative, then electrolytic cell it's the complete opposite. So in electrolytic cell, the anode is positive. Okay, let's look at another example. Here we have the lead bromide. So it's molten lead bromide, so ions present are only these two. So you're going to do your half equation for both terminals, combine them to form your ionic equation. And from there you can see it's from the ions to gas. So you can see brown gas is released at the anode. As you can see here, from the ions it turns into the metal. So gray solid is deposited at the cathode. Ta-da! You can see bromine gas is produced for the product. Or you can also say lead metal. Or you can say both. I think they'll ask both most of the time. Unless you specify the question, hey, what is produced, what's the product at the anode, let's say. Here is example 3. And you guys can take a screenshot of this because I'm not going to explain it. 3, 2, 1, okay. Now let's get into the 3 factors of when it comes to electrolysis.